and dump. Now you may think that this is the end, and it is. All right. So, enthalpy of a formation. Enthalpy of formation is when you build things from their elements. Okay? So hydrogen combines with oxygen to make water. In this case, it's liquid water, so we have a standard enthalpy of formation of negative 285.8 kilojoules per mole. Down here, we're combining hydrogen and oxygen to make gaseous water, with a standard enthalpy of formation of negative 241.8 kilojoules per mole. And then finally, we combine 6 moles of graphite with 3 moles of oxygen and 6 moles of hydrogen to make glucose, with a standard enthalpy of formation of negative 1,273 kilojoules per mole. So in every single case, the compound in question is being built from the pure elements in their standard state. So hydrogen is a gas, oxygen is a gas, carbon is graphite, and so on. You'll also notice that we have fraction coefficients. That is standard for enthalpies of formation because we want to produce only one of our product. Okay, so we're producing 1 mole of liquid water, 1 mole of gaseous water, 1 mole of glucose. Okay? Always, always, always 1 mole. And if that means you have to have fractional coefficients on the reactant side, then so be it. You'll also notice that we're only building the one compound, okay? Nothing else. And it doesn't really matter if these reactions are feasible or not. I mean, it's not really practical or feasible for us to make glucose from the pure elements. That's not really a thing. These are kind of a fiction, but not really, because, well, we'll get to that in a minute. The way we use them means that it doesn't matter that this isn't really something that can happen. But we have big standard enthalpies of formation tables. This here is this is a very small table. Just a list of compounds in alphabetical order showing their enthalpy of formation in standard conditions. So in this case, they tell you that standard condition means 25 degrees Celsius or 298 Kelvin. So if you go in your textbook, there is a table at the back of your textbook that has not just enthalpies of formation, but also entropy and Gibbs free energy, just all the numbers that are common and important in thermodynamics. Before the internet, it was standard for chemists to have these really freaking huge books that consisted of just table after table after table of numbers describing and compounds like this. And nowadays, we do have the internet, and that makes things a little bit easier. So, how are we going to be using these enthalpies of formation? Okay. So, this is another application of Hess's law. Okay. The appropriate reactions for a Hess's law problem aren't always there. The reactions that we looked at in the last set of slides in set 66, or 65, the Hess's law lecture, those are, it's just, you might not have a set of reactions that will go from the reactants you want to the products you want, but the elements are always there. So what we do is we set up this fiction that in order to get from reactants to products, you break the reactant compounds down into their elements, and then you take those elements and build them back up into your products. Again, this is purely a fiction, but this is a state function we're talking about, so it doesn't matter that you can't actually go from reactants to elements and then from elements to products. What does matter is that this path, if you could take it, would get you from A to B, and therefore the energy change going from reactants to elements, then elements to products, does work. Now, how do they measure these enthalpies of formation? Well, that probably involves a little bit of work with, Hess's law stuff, where, they are able to do things like this, reacting hydrogen and oxygen to get water. That is something you can do. And then you can react carbon with oxygen. Dang, cat. You can react carbon with oxygen to get carbon dioxide. And then you can combine glucose with oxygen to get carbon dioxide and water. And, you can just do the Hess's law problem from there. And that allows you to get this semi-fictional reaction of carbon plus oxygen plus H2 gets you glucose. So no matter what, we'll always be able to use the enthalpy of formation to work this sort of problem, going from reactants to elements, then elements to products. Let's see how we do that. So here's that exact reaction I was talking about. There's glucose plus oxygen makes CO2 plus H2O. So glucose, we break it down into its elements. So 6 carbon plus 6 hydrogen plus 3 oxygen, right? And the enthalpy change for that particular reaction is the negative of the enthalpy of formation for glucose. Okay? We've just flipped the reaction around. You flip the reaction, you flip the sign. Now, oxygen is already an element, and this is an important point, something that you need to know. If it's an element in its native state, then the enthalpy of formation is 0. Now, we take these elements that we have up here, the carbon, the hydrogen, and the oxygen, and we combine them. So we combine 6 carbon and 6 oxygen to make 6 CO2. Why 6 CO2? Because we need to make 6 carbon dioxides on the right. So that will give us 6 enthalpies of formation for carbon dioxide. And then we do the same thing with water. 6 hydrogen, that's 3 oxygen to make 6 water. That means that the enthalpy change for this particular reaction is just 6 times the enthalpy of formation for water. Okay? So the enthalpy change of the reaction that we're looking at, glucose plus oxygen makes CO2 and H2O. It's going to be enthalpy change for the first reaction, breaking up glucose, plus the enthalpy change of the second reaction, combining carbon and oxygen to make CO2, plus the enthalpy change of the third reaction, combining hydrogen and oxygen to make water. So those 3 reactions were, with their enthalpies, I should say, the enthalpies of those reactions are the negative enthalpy of formation of sugar, plus 6 times the enthalpy of formation of water, plus 6 times the enthalpy of formation of CO2. Or, to put it another way, 6 times water plus 6 times CO2 minus sugar, aka the products of your reaction minus the reactants. Okay. These enthalpy of reactions, this is always going to have this form, products minus reactants. For any reaction, so long as you can find the enthalpy of formation for every product and every reactant, then it's going to take this somewhat complicated looking form. Products minus reactants. You multiply the enthalpy of formation for every reactant and product by the number of moles, the coefficient from the reaction, the number of moles that you have of that product or reactant. And then you add all your products together, you add all your reactants together, then it's products minus reactants. Okay. So, for example, calcium carbonate breaking apart into calcium oxide and carbon dioxide. So, that's okay. So, here's a reaction. Calcium carbonate, solid, breaks apart into calcium oxide, solid, plus CO2, gas. So we look at this table of enthalpies of formation. Here we have calcium carbonate. The enthalpy of formation for calcium carbonate, let's do this, negative 1,207.1. For calcium oxide, it is right below it, negative 635.5. Carbon dioxide is right below that, negative 393.5. Okay. So it's going to be products minus reactants. So delta H equals negative 635.5 plus negative 393.5 minus our reactants, negative 1207.1. So we add these two together. It's 0.0992, carry the 1, 0, 1, negative, minus negative 1207.1. One is the loneliest number that you'll ever do. So our answer is positive 178.1 kilojoules. In other words, in order for this reaction to happen, you're going to have to pump in 178.1 kilojoules of energy. It is an endothermic reaction. And yeah, that's how it works. You heat up calcium carbonate and it will decompose into calcium oxide and carbon dioxide. So that one was pretty simple because 1, 1, 1. So let's look at the next one. Taking glucose and combining it to make sucrose and water. You might remember from, you guys can hear the dog chewing on his bone. Hopefully it's not too much of a problem. You might remember from biology classes that this is a dehydration synthesis because you're adding two things together and losing water. All right, so let's do this reaction. 2C6H12O6. Okay, now he's chewing on his bone, his rubber bone. Combines to make C12H22O11 plus H2O. And this is important. Solid, solid, liquid. Okay. So, sugar, glucose, where are you at? There you are. Negative 1273. Negative 1273. Sucrose, where you at? Okay, solid. Negative 2221. And then water. The reason why it's important to specify the state of matter is because liquid water is 285.8, gaseous water is 241.8. Okay, so it would change the answer, and you could get the answer wrong. So because this is a liquid, it's negative 285.8. Okay, so enthalpy change of our reaction is products minus reactants. So 1 times negative 2221 plus 1 times negative 285.8 minus 2 times negative 1273. Okay. Because we break apart, or we combine 2 moles of glucose in order to make our sucrose. And now this time, rather than making you watch me do all of that math by hand, I'm just going to open up Mr. Calculator. All right. Okay, so now I'm going to be a little bit more careful about our signs. 2221 plus, no, not positive 22. Dang it. 2221 negative plus 285.8 negative minus 2 times 1273, also negative. Means that the enthalpy of reaction for this reaction is positive 39.2 kilojoules. All right. So this reaction is also endothermic, but it's less endothermic. You have to put in energy to make this happen, but not as much. Okay, and our third reaction, closing this down and jumping over to this so my calculator goes away. Now we are combining methane to make propane and release some hydrogen. So, once again, three methane gas plus, oh, nope, just combine to yield 1 propane gas plus 2 hydrogen gas. So our product, our reactant is methane. Methane is right here, negative 74.8. They will not ask you to memorize these numbers. That would be kind of absurd. They'll always have to provide you with these enthalpies of formation. Propane, negative 103.85. And hydrogen. Hydrogen is not on here. It doesn't need to be on here. It's a pure element in its native state, so it's 0. So the enthalpy change for our reaction is products minus reactants, final minus initial. It's going to be 1 times negative 103.85 plus 2 times 0, just being thorough, minus 3 times negative 74.8. Okay. Is negative 120.6. Really? That seems wrong. But I guess it's not. I mean, those are the numbers. 1 of those, 3 of those. Now let's see. Let's be more careful. 103.85 negative minus 3 times 74.8, also negative, equals, yeah, okay, good. See, you guys don't have that intuition. You would have just accepted that. I mean, if I treat them both as positive, it should give the same answer as if I treat them both as negative, but I guess not. Well, no, I flipped the sign, so obviously it is not it's not proper, it's not correct. So positive 120.6. Yeah, building from a smaller molecule to a bigger molecule like that, I would expect it to be endothermic, which is why I had to stop and double check. Anywho, so those are enthalpy of formation problems. You have a table with your numbers in it, and you get a whole lot of things. So now we have 3 more problems. Go ahead, pause, try and work through these using the tables of numbers in your textbook. And I will now open that up as well, because I should have done that earlier, but I am a doofus. So the table of numbers in your textbook is, okay, I'm getting there. I have to click so many links. There's the song that never ends. Music goes on and on, my friends. Some people started singing and not knowing what it was, and now they stuck singing it forever just because this is the song that never ends. Yes, it goes on and on, my friends. Be kind to your web-footed friends, for a duck may be somebody's mother. Be kind to your friends in the swamp. All right, so the tables we're looking for are in the back. Appendix, thermodynamic properties at 25 degrees Celsius. A10. So you see that there's other properties. We'll get to those a little bit later. Tomorrow night I'll cover those in those lectures. But you see they're listed sort of alphabetically by element. So aluminum, which gives us a solid aluminum, gaseous aluminum, aluminum chloride, and aluminum oxide. Barium solid, barium gas, barium 2+, barium chloride, barium oxide, barium carbonate, barium sulfate, and so on. So what we need to find at the moment, where did it go? No, that's not the one I want. There we go. All right, so now we need to find water, sulfurous acid, and water. Oh no, that's hydrogen peroxide, excuse me, and sulfurous acid to make water and sulfuric acid. And again, note the states: liquid, aqueous, liquid, aqueous. So I'm going to, first thing, rewrite the reaction so that I have it available to me even as I look through this stuff. Plus H2SO3 aqueous yields H2O liquid plus H2SO4 aqueous. All right. So now we go back to our big table O numbers. And let's go ahead and find, well, let's see, hydrogen. That's probably a good place to look for things. Hydrogen, we have liquid water. Okay, so liquid water is negative 285.8. And we have hydrogen peroxide. We do, negative 187.8. Acid. The sulfuric acid is probably under sulfur. And it, oh dear, it doesn't have sulfurous acid. That's a shame. Okay, so the sulfuric acid is negative 909.3. Okay, so let's see. That's shocking. Oh, not too shocking. People don't work with sulfurous acid, enthalpy of formation. No, I didn't mean sulfuric acid, Mr. Googlebox. Nope, that's a totally different compound. Dang it, NIST. Sulfurous acid, there we go. So, I'm looking for thermodynamic. This might be under chemical and physical properties. Nope. Spectral, related records, chemical vendors, food additives, toxicities. Spectral, no, I don't, it's not going to be spectral information. Let's see. You have failed me, Pubkim. Now you must die. Experimental properties. Physical description, liquid, human metabolism, no. All right, let's... Okay, I'm going to try, ooh, maybe this is going to be kind of a leap. Yep, didn't exactly expect it to be, Okay, so do they have NIST? They don't. Okay, so what I'm going to do is I'm going to come back up here. NIST, the web book, is really helpful. H2SO3. Really? Oh. Okay, let's go by name. looking for is thermodynamic in the condensed phase. Maybe it's sulfurous acid. How? Not sulfuric acid, sulfurous acid. Do they have related compounds? They don't. H2O4S? That's a weird way to do that. Okay, so let's try H2O3S. Okay. Screw it. These are all 1-to-1 to 1-to-1 anyway. I'm sure that was a really fascinating bit of... Okay, so I'm just going to make something up. Negative 800. All right. So 1-to-1 to 1-to-1. So products minus reactants. 285.8 negative plus 909.3 negative minus 800 negative minus 187.8 negative. So with that, our products minus our reactants, so delta H equals negative 285.8 plus negative 909.3 minus negative 187.8 plus negative 800 equals negative 207.3 kilojoules. If this were a possible reaction, it probably isn't, then it would be exothermic. That was an annoying and boring thing. I am sorry about that. So what I'm going to do right now is deleted. I'll never have to go through that again, and neither will anyone else. All right, so now let's do copper sulfide, copper 2 sulfide, plus iron yields copper plus iron 2 sulfide. So, well, CuS, solid, plus Fe, solid, yields Cu, solid, plus Fes, solid. Okay, now we look for, there's that. So, we're going to have to go back a couple of pages to find iron and copper, because if iron and copper sulfide are listed in here, they'll be listed, yep, copper sulfide, negative 53.1, and iron sulfide, iron 2 sulfide, they don't have iron 2 sulfide, they have iron 4 sulfide, but they don't have iron 2 sulfide. Okay, so I'm going to go ahead and executive decision, change that. So we need 2 of those, so 2 of those, and 2 of those. Okay, and anyway, this makes this a more interesting problem. All right, so for the iron 4 sulfide, which is wild, they have FeS2, but not Fe2S3, not FeS. That's... okay, negative 178.2. Now, what about these other two? What about iron and copper? Again, elements in their native states, so 0 and 0. Okay. The enthalpy of formation of an element in its native state is always 0. So now we do this. Delta H, products minus reactants, so 1 times negative 178.2 minus 2 times negative 53.1. So 178.1 negative minus 2 times 53.1 negative equals negative 71.9 kilojoules. Got to include those units. All right. Now again, I'm going to have to edit this. So 2, 2, 2. All right. Otherwise, can't use your textbook. Okay. C2H6 plus O2 yield C2H2 H2 plus 2H2O. Okay, so this is gas, 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 gas. All right, so basically we're taking ethane, combining it with oxygen to make acetylene and water, which I'm pretty sure will never, ever happen. But now we're going to need to dig into carbon, because ethane and acetylene would both be under carbon. Or maybe they wouldn't. Oh, I hope they have organic compounds in here. I skipped right over hydrogen. Do they have them? They do not have them under hydrogen. Oh my god, I just realized that these numbers probably are available on the previous page of my slide. Or they're right there. You can't use your textbook, but you can use the table I very conveniently included on the very next page. Or can you? Is sulfurous acid on there? I don't. Yes, it is on there. It's negative 608.8. And this says sulfuric acid is negative 814, not negative 909. Well, whatever. Okay, so we'll go ahead and use this very convenient table. C2H6 is negative 84. Like I said, they'll always give you the numbers. Oxygen is 0. Acetylene is positive 227.4. And water, liquid, no, gaseous water, not a liquid. Gaseous water is negative 241.8. They'll always provide you the numbers. And I did provide you with the numbers, even though I'm a doofus and forgot that. Okay, so products minus reactants. 227.4 plus 2 times negative 241.8 minus negative 84.0 plus 0. All right. So 227.4 plus 2 times 241.8 negative minus 84 negative equals negative 172.2 kilojoules. So this would be an exothermic reaction, which is kind of surprising, actually. I wouldn't have expected that. Okay. Good. All right, so those are enthalpy of formation problems. Those will be useful to you on this week's lab, so I'm glad I was able to get to it tonight so that you'll have this video available for Sunday. And that's it for this set of slides. So I will be back in a few minutes to talk about bond enthalpy, when I once again will have to reiterate that a foolish consistency is the hobgoblin of little minds. See you then.